Insulating bearing stands in older motor installations served several purposes. Firstly, insulating the bearing stands allows for electrical isolation between the motor and the ground. This prevents stray currents from flowing through the bearings, which could cause damage. Bearing currents are stray electrical currents that flow through the bearings of electric motors and generators. They can cause pitting, fluting, and eventual failure of the bearings. These currents arise due to several factors, including electromagnetic fields within the motor, inverter drives, and grounding issues. When a motor operates, the alternating current flowing through the stator windings creates electromagnetic fields. These fields can induce voltages in the rotor and the motor frame. If there is a path to ground through the bearings, current will flow. Variable frequency drives, or VFDs, are commonly used to control the speed of electric motors. However, they can also introduce high-frequency switching voltages, which can lead to bearing currents. These high-frequency voltages can capacitively couple to the rotor, creating a voltage potential between the rotor and the stator. When this voltage discharges through the bearing, it causes electrical erosion. Inadequate grounding practices can also contribute to bearing currents. If the motor frame is not properly grounded, stray currents can find their way through the bearings to ground. This is particularly problematic in older installations where grounding methods may not be as robust as modern systems. The effects of bearing currents can be severe. Electrical discharge machining, or eddy, occurs as current passes through the bearing. This creates tiny pits on the bearing surfaces. Over time, these pits can coalesce to form fluting, which are washboard-like patterns on the bearing races. Fluting increases noise and vibration and ultimately leads to bearing failure. The increased friction and weight caused by bearing currents also reduce the lifespan of the bearings, leading to more frequent replacements and increased maintenance costs. There are several methods to mitigate bearing currents. Insulation can be installed to interrupt the electrical path through the bearings. This can be achieved by using insulated bearings or by coating the bearing housings with a non-conductive material. Grounding brushes can be used to provide a low impedance path for stray currents to ground, bypassing the bearings. These brushes are typically made of carbon or graphite and are mounted on the motor shaft. Common mode chokes can be installed on the output of variable frequency drives to reduce high-frequency voltages that contribute to bearing currents. These chokes filter out the high-frequency components, preventing them from reaching the motor. It is important to ensure that the motor frame is properly grounded to provide a safe and effective path for stray currents to ground. This helps to minimize the risk of bearing currents. Regular monitoring of bearing temperature and vibration can help to detect early signs of bearing damage caused by electrical currents. This allows for timely maintenance and prevents catastrophic failures. Secondly, rotating machines can generate eddy currents in the surrounding metal structures. Insulating the bearing stands helps minimize eddy current losses and prevents them from causing heating or noise issues. Eddy currents are circulating currents induced in conductive materials when they are exposed to a changing magnetic field. These currents flow in closed loops within the material, similar to eddies in water. Changing magnetic field can be produced by alternating current flowing through nearby conductors or by the movement of a magnet relative to the conductor. According to Faraday's law of induction, a changing magnetic field induces a voltage, or electromotive force, in a conductor. This voltage drives the flow of current within the conductor. The magnitude of the induced voltage is proportional to the rate of change of the magnetic field and the area of the loop in which the current flows. Eddy currents flow in a direction that opposes the change in the magnetic field that produced them, according to Lenz's law. This opposition results in energy dissipation in the form of heat due to the electrical resistance of the conductor. The amount of heat generated is proportional to the square of the current and the resistance of the material, as described by Joule's law. The magnitude of eddy currents depends on several factors, including the strength and frequency of the magnetic field, the conductivity and permeability of the material, and the geometry of the conductor. Materials with high conductivity, such as copper and aluminum, tend to have larger eddy currents. Similarly, materials with high permeability, such as iron and steel, can concentrate magnetic fields, leading to increased eddy currents. Eddy currents can have both beneficial and detrimental effects. In some applications, they are intentionally generated and utilized for specific purposes. For example, eddy current brakes use eddy currents to slow down moving objects, such as trains or amusement park rides. Eddy current testing is a non-destructive testing method that uses eddy currents to detect flaws and discontinuities in conductive materials. Induction heating uses eddy currents to heat materials for various industrial processes, such as heat treatment and melting of metals. However, in many applications, eddy currents are undesirable because they cause energy losses and heating. For example, in transformers and electric motors, eddy currents in the core material can lead to significant energy losses, reducing the efficiency of the device. These losses manifest as heat, which can damage the insulation and other components. There are several methods to minimize eddy current losses. Lamination involves dividing the conductive material into thin layers, or laminations, that are electrically insulated from each other. This reduces the size of the loops in which eddy currents can flow, thereby increasing the resistance and reducing the magnitude of the currents. Using materials with high electrical resistivity can also reduce eddy current losses. Materials such as ferrites and amorphous metals have relatively high resistivity compared to conventional metals like iron and steel. Optimizing the geometry of the conductor can also help to minimize eddy current losses. For example, using a toroidal core in a transformer can reduce the magnetic flux leakage and thereby reduce eddy currents. In summary, eddy currents are circulating currents induced in conductive materials by changing magnetic fields. They can cause energy losses and heating in various applications, but can also be utilized for beneficial purposes in certain technologies. Thirdly, insulated bearing stands can reduce noise transmission from the motor to the ground and surrounding structures. This can improve the overall noise environment in the motor room. Noise transmission refers to the process by which sound waves travel from one location to another through various mediums. This phenomenon is a significant consideration in architectural acoustics, environmental noise control, and the design of mechanical and electrical equipment. Sound waves are vibrations that propagate through a medium such as air, water, or solid materials. When a sound source generates these vibrations, they radiate outwards in all directions. As these waves encounter different materials and structures, they can be transmitted, reflected, absorbed, or diffracted. The transmission of sound waves depends on several factors, including the properties of the medium, the frequency of the sound, and the geometry of the structures involved. Different materials have different abilities to transmit sound. For example, dense, rigid materials like concrete and steel tend to transmit sound more effectively than lightweight, porous materials like foam and fiberglass. The frequency of the sound also affects its transmission. High-frequency sounds tend to be more easily blocked by barriers than low-frequency sounds, which can diffract around obstacles. The geometry of the structures involved plays a crucial role in sound transmission. Sound waves can travel through openings such as doors and windows and can also be transmitted through walls, floors, and ceilings. The design of these structures can significantly impact the amount of sound that is transmitted. There are several mechanisms by which sound waves can be transmitted through structures. Airborne sound transmission occurs when sound waves travel through the air and pass through openings or gaps in a barrier. Impact sound transmission occurs when vibrations are generated by direct physical contact with a structure, such as footsteps on a floor. Structure-borne sound transmission occurs when vibrations travel through solid materials, such as walls and pipes. To control noise transmission, various techniques can be employed. Sound isolation involves creating barriers to block the passage of sound waves. This can be achieved by using dense, airtight materials and by sealing gaps and openings. Sound absorption involves using materials that absorb sound energy, reducing the amount of sound that is reflected or transmitted. Vibration isolation involves decoupling vibrating equipment from the surrounding structure to prevent the transmission of vibrations. Damping involves adding damping materials to structures to reduce vibrations and noise radiation. In architectural acoustics, sound transmission is a critical consideration in the design of buildings and rooms. The goal is to create spaces that are comfortable and functional by controlling the amount of noise that enters or leaves the space. This involves careful selection of materials, design of structural elements, and implementation of noise control measures. In environmental noise control, sound transmission is a key factor in assessing the impact of noise sources on the surrounding environment. This involves measuring and modeling noise levels and implementing strategies to reduce noise propagation. In the design of mechanical and electrical equipment, sound transmission is an important consideration in reducing noise levels and improving the performance of the equipment. This involves using vibration isolation techniques, damping materials, and noise enclosures. In summary, noise transmission is the process by which sound waves travel from one location to another through various mediums. It is a complex phenomenon that depends on several factors, including the properties of the medium, the frequency of the sound, and the geometry of the structures involved. Controlling noise transmission is essential in architectural acoustics, environmental noise control, and the design of mechanical and electrical equipment. Fourthly, insulating the bearing stands allows for better ground fault detection and protection. If a ground fault occurs, the insulated stands help prevent the fault current from flowing through the bearings and damaging the motor. Ground fault detection and protection are critical safety measures in electrical systems designed to quickly identify and isolate ground faults, thereby preventing electrical shock, equipment damage, and fire hazards. A ground fault occurs when an unintended electrical path is established between a live conductor and ground or a grounded object. This can happen due to insulation failure, accidental contact with the grounded surface, or other unforeseen circumstances. When a ground fault occurs, a large amount of current can flow through the unintended path, posing a significant safety risk. Ground fault detection involves continuously monitoring the current flowing in the electrical system to detect any imbalance that indicates a ground fault. There are several methods for ground fault detection. Ground fault circuit interrupters, or GFCIs, are commonly used in residential and commercial settings to protect against electrical shock. They monitor the current flowing in the hot and neutral conductors of a circuit. If there is a difference of more than a few milliamperes between the two currents, the GFCI trips the circuit to cut off the power. Ground fault relays, or GFRs, are used in industrial and commercial settings to protect equipment from ground faults. They monitor the current flowing in the grounding conductor. If the current exceeds a predetermined threshold, the GFR trips the circuit, isolating the fault. Zero-sequence current transformers, or ZSCTs, are used to detect ground faults in three-phase systems. They encircle all three-phase conductors and the neutral conductor. Under normal conditions, the currents in the three phases cancel each other out, resulting in zero net current. However, when a ground fault occurs, the currents become unbalanced, and the ZSCT detects the resulting current. Ground fault protection involves taking action to mitigate the effects of a ground fault once it has been detected. This typically involves stripping a circuit breaker or switch to isolate the faulted circuit. Ground fault protection is essential to prevent electrical shock, equipment damage, and fire hazards. When a ground fault occurs, the sudden surge of current can cause severe electrical shock to anyone who comes into contact with the faulted equipment or the ground. Ground fault protection quickly disconnects the power, reducing the risk of electrical shock. Ground faults can also cause significant damage to electrical equipment. The high current can overheat conductors and insulation, leading to equipment failure. Ground fault protection prevents equipment damage by quickly isolating the fault. Ground faults can also ignite flammable materials, leading to fires. Ground fault protection reduces the risk of fire by quickly disconnecting the power. To ensure effective ground fault detection and protection, it is important to properly design and install the electrical system. This includes using properly sized conductors, providing adequate grounding, and installing appropriate ground fault protection devices. It is also important to regularly test and maintain the ground fault protection system to ensure that it is functioning properly. This includes testing GFCIs and GFR on a regular basis. In summary, Ground fault detection and protection are critical safety measures in electrical systems designed to quickly identify and isolate ground faults, thereby preventing electrical shock, equipment damage, and fire hazards. They involve continuously monitoring the current flowing in the electrical system to detect any imbalance that indicates a ground fault and taking action to mitigate the effects of the ground fault. Fifthly, in some cases, insulating the bearing stands may be necessary to align the motor properly or to provide insulation between the bearings and other components. Proper motor alignment is critical for ensuring efficient and reliable operation of machinery in a wide range of industrial applications. Misalignment can lead to increased vibration, excessive wear and tear on components, and premature equipment failure. Motor alignment involves precisely positioning the motor and the driven equipment, such as a pump, fan, or compressor, so that their rotational axes are collinear. This ensures that the power is transmitted smoothly and efficiently from the motor to the driven equipment. There are two primary types of misalignment: parallel misalignment and angular misalignment. Parallel misalignment occurs when the rotational axes of the motor and the driven equipment are parallel but offset from each other. This means that the center lines of the two shafts are not aligned. Angular misalignment occurs when the rotational axes of the motor and the driven equipment are not parallel. This means that the shafts are at an angle to each other. Both types of misalignment can cause significant problems. Misalignment can lead to increased vibration, which can damage bearings, seals, and other components. It can also cause excessive wear and tear on couplings and other mechanical components. Misalignment can also reduce the efficiency of the system, leading to increased energy consumption and higher operating costs. Proper motor alignment can provide several benefits. It can reduce vibration, which can extend the lifespan of equipment and reduce maintenance costs. It can also reduce wear and tear on components, further extending their lifespan. Proper alignment can also improve the efficiency of the system, reducing energy consumption and lowering operating costs. There are several methods for achieving proper motor alignment. Straight edge alignment is a simple method that involves using a straight edge to align the shafts of the motor and the driven equipment. This method is suitable for small machines with low operating speeds. Dial indicator alignment is a more precise method that involves using dial indicators to measure the misalignment between the shafts. This method is suitable for larger machines with higher operating speeds. Laser alignment is the most accurate method for aligning motors. It involves using a laser beam to measure the misalignment between the shafts. This method is suitable for critical applications where high precision is required. The process of motor alignment typically involves several steps. Firstly, the equipment should be inspected for any signs of damage or wear. Any damaged or worn component should be replaced before proceeding with the alignment process. Secondly, the motor and the driven equipment should be roughly aligned by eye. This involves positioning the equipment so that the shafts are approximately collinear. Thirdly, the precise alignment should be measured using one of the methods described above. Finally, the motor should be adjusted until the misalignment is within acceptable limits. It is important to regularly check and maintain motor alignment to ensure that the equipment continues to operate efficiently and reliably. Alignment should be checked after any maintenance or repair work that involves disconnecting or moving the motor or the driven equipment. In summary, proper motor alignment is critical for ensuring efficient and reliable operation of machinery. Misalignment can lead to increased vibration, excessive wear and tear on components, and premature equipment failure. Proper alignment can reduce vibration, extend the lifespan of equipment, and improve system efficiency. The last bearing stand was not insulated because it was the grounding point for the motor frame. This configuration was common in older motor installations but is less common today due to advancements in motor design and protection systems. Reliance Electric may not have been familiar with the specific design considerations for this particular motor and mill setup.